have it. Yeah. Yeah, so today I'm going to talk to you about a paper of mine that is leveraging uh, some machine learning approach for efficient and low resource NLP. And specifically, this one is trying to use the concept of epistemic uncertainty to be able to produce better models that are generalizable, that generalize better while requiring way less data. Um, yeah, so that's roughly about it. We go through it together. So, as a bit of contextualization or context, if I can say so, you can assume that here we want, for instance, we have a pre-trained models, like it can be anything that you think of. It can be um, with Tvec, XLSR, it can be um, WaveLM, it can be Hubert, or it can also be some commercial networks like Nemo or like the, yeah. And you want to adapt them to new and diverse languages. It can also be accents and everything. But then there is a problem because those languages are low resourced, if I can say so. They have very limited label data, and we know that in the deep learning field, I mean, very big breakthrough, for instance, in English, have been achieved by increasing the size of the data set, like more data, and also scaling the network's size. So in this situation, you have very low and limited label data. And the languages, they are highly morphological and complex. And, you know, you have lots of like unlabeled data, but you don't have enough budget, for instance, to label them because it's expensive. Like for people to listen to those using transcribe, put down whatever has been said in those languages using those accents in um, is actually expensive. It's not um, easy. It's not a trivial task. So the idea now is about how we can uh, cope with the current data scarcity, the fact that we have very small labeled data, and how we efficiently use that small data to maximize, to still build and adapt properly our pre-trained ASR models to the new language or the new accent that we are interested in, and also the new domains. By doing so, we want also to reduce the cost of annotation because if we are able to build something that a model that is robust enough, then we can have some insurance that we are going to have to some extent some high quality leveling, and that will also reduce the cost of annotation and the demand for human label, human annotation. And obviously, everything coming together as also increasing the model's robustness and like generalization. We want the model across different domains and across different settings to be able to perform pretty much well. So yeah, those are the main questions that we are trying to solve. To bring a solution to. So to do this, we bring together two concepts, two machine learning concept. I would say the first one is what we call active learning, and the second one is uncertainty quantification. So I'm going to describe first of all active learning, which is something that hasn't been extensively explored in the context of like NLP, and even less for low resource languages. So you can look at active learning is usually described as a type of like semi-supervised learning algorithm where you have a model that you are trying to optimize, but in a much smarter way because you start from a very small set of labeled data. You have a very big set of unlabeled data that is usually called a pool. So from that pool, you're trying to make the model learn which sample specifically is going to be more informative for the models to improve and to maximize its performance. So that model that we also call here the learner does this by actively querying, let me say, like here I wrote authority source called Oracle to learn the correct prediction for a given task or problem. So one interesting aspect or one interesting goal is that with AL or active learning, we also want to speed up the process of the the learning task or the learning process, especially when we have like very small data and we need actually data, because at the end of the day, even if we are doing some pre-training, most of the useful tasks are mainly at the end of the day are mainly supervised tasks. Like if you think about ASR, if you think about machine translation, if you think about information retrieval, name entity recognition, those type of things, they are mainly supervised. So as I said, there have been some very few studies in active learning for NLP, and some of them have highlighted the fact that we could actually achieve high accuracy around 98, 99 accuracy while requiring only 20% initial label data set. And this is actually very interesting and very crucial in the context of African NLP, but more generally in the context of like low resource languages. It can be expanded to any other language. Whereas, for instance, if we compare to traditional methods, we have, for instance, the need of at least 50% of the labeled data, for instance. So, second, in this work, actually, what we are trying to do is to bring those two ideas together. So I talked earlier about the uncertainty quantification. So here, the uncertainty quantification is a little bit more, I would say, Bayesian related. So there are many type of like uncertainty. So there's aleatoric uncertainty and there's like epistemic uncertainty. So performing some uncertainty quantification analysis is just a way of learning how the model behaves in some situations. It is about, for instance, if we focus on epistemic uncertainty, it is the uncertainty of the model, which is primarily due to the lack of knowledge or of like the lack of data, for instance. So in those setup, we assume that hey, if we expose the model to more data, then it's gonna get better. And then there's also the aleatoric uncertainty, which is the opposite actually. Yeah, so there are many ways, for instance, to work on the uncertainty quantifications, and I'm going to describe it here. So we focused on, obviously, because the task was ASR, we have the evaluation metric, which was like the water rate. We built something that we called the uncertainty water rate, which is technically which is technically getting the uncertainty over a speech given the different predictions. And you're going to understand why I'm saying given the different prediction. So to compute the epistemic uncertainty, there are many ways, but two of the most famous ones are MC dropout and deep ensembles. But then deep ensembles, you can imagine as like having a, let me say, a set of n different models. They probably have the same architectures, but they are initialized randomly. So the weights, the initialization are different. So at the end, you have some more or less different weights, and you take the predictions over of an input over those different models, and then you can, for instance, take the variance or the standard deviation or things like that. With MC dropout, something is a little bit different because what you are acting on is, for instance, is the Monte Carlo dropout. So roughly, this is in practice done by switching on at inference time, because usually at inference you don't switch on the dropout, but then with MC dropout you switch on at inference time the dropout layers. That means that if you, for instance, run on the same input the model n times, you are going to have high likely n different results. They might be close, they might be entirely different, but then you have n different output. So in this case, for instance, we can say that we will have n different speech representations that are going to be used to predict, for instance, the transcript. So since the speech representation are going to be different, then the predicted transcriptions could also be different. And then obviously in this case we have a target, so we compute the whatever rate with respect to the target using each of the predicted transcriptions given each different speech representation, and then we take, for instance, the variance over. That is what can tell us for what can that is what can be used, for instance, to tell us how uncertain about that specific audio the model is. So ideally, the model should be robust enough so that regardless of those different fluctuations, those different neurons that are turned on and off during that process, it produces like more or less the same representation that leads to more or less, if not the same, transcription. So the advantage here is that MC dropout actually helps quantify, as I was saying, the model uncertainty, but does not sacrifice the computational complexity or the test accuracy, and can be used in any type of models that are trained, and this is important, that are trained with dropout. That's why, for instance, there are some models like Whispers will be disqualified because for instance, Whisper Base doesn't have that dropout component. Only Whisper Large has it, but Whisper is a very big language, very big ESR model. So, if computational resources is an issue, then you can run a Whisper with this approach. And obviously, what we did was to select, for instance, the top K. We selected the most uncertain one, and then we selected also randomly, and we tried to leverage how well the model was doing. Obviously, we have some baselines, and the baselines were technically taken and throwing to the model as we usually do. Like if you have a data set, what you usually do, for instance, if you have a pre-trained model, what you usually do is you take the entire data set, label data set, and you throw it to the model. Obviously, you split it across train, dev, and like test, and you then throw that to the model, and then you train, you fine tune the model. But so that's our baselines here. But in this setup that we are trying to build, what we've done was a little bit different because we put ourselves in the context where we have data constraints. So it aligns with like real life settings where, for instance, you might have some data, but then the data will not be feasible, will not be usable, or you might actually not have data. So what we've done was like to constrain ourselves to not go over 65% overall. So initially we start, for instance, with 30% of the label data set, and everything else was considered. We have two different setups. The first one in which we had everything that was considered as is, like as labeled. So we just learn the model to know which samples to select from, to choose given the target. And the second aspect is where, for instance, we simulate an active learning framework where the speech do not have any predicted any like gold transcription or like target. So yeah, overall that's what we did, and then it allows us to use relatively 45% less of the data to do the training, as opposed, for instance, to the baselines. So we use for this task, for this project, we use the Afri Speech 200 dataset, which is a African-centered dataset that has been built for clinical and general domain ASR. That was presented. It was accepted at TACOL, and then that was presented recently at EMNLP. In here, we have, as the name indicates, 200 hours of recording that were built upon almost 70,000 audio clips. We got almost 2.5 thousand unit speakers that were spread across 120 languages in different accents. And this is the first clinical for medical detection, to be more specific, and general ASR domain on African accented speech. So here I've put the different details of the data set, the split per gender, per age, the repartitions, the split as well for across the different domain, clinical and general, and how we also split the audios across the different splits of the models, like the train, the testing, dev, the number of speakers, the testing, the dev, and the train set, the number of accents, and all those type of things. So we made sure that this situation simulate as much as possible real life situations, but we also didn't want to introduce too much of a bias in the process. So we try as much as we can to keep everything like really balanced and really like realistic close as much as possible to the real world situation. So this is an overview of the system, of the approach that we've built. And it is actually inspired from one of my previous work that was leveraging active learning for multilingual pre-trained language models for 23 African languages, presented last year, I think, at EMNLP. So the idea is more or less the same. So here we have the initial data, as I was telling you, that we split into two, train and testing. We use a pre-trained ASR model that we fine-tune with the 30% of data. Now, after we obtain obviously a model that is like more contextualized, and we test. Technically, we use the 70% remaining data to predict the different transcriptions across the different speech of the augmentation set. That's how we called it, augmentation set. So given this augmentation set and given those speeches, we have different predictions. And as I was explaining earlier, so we have two settings. The first one, which was where this augmentation set was actually, let me try to zoom a little bit. This augmentation set was actually labeled, so like supervised. So in that case, we use MC dropout, and then we have n different speech representation that gave us n different transcripts, and then we use the predicted transcript, compared it against the target, got the word error rate, and then we took the standard deviation of the word error of those word error rates to compute the uncertainty of the model given that input speech. In the second situation, where we were in a more active learning situation phase, and we assume that we don't have a good label, we don't have target. The situation was a little bit different, so we have to be more ingenious about it. So that means this the first part about the MC dropout remains the same. We have 10 different for here we use 10 MC dropout rounds, so we have 10 different speech representations, and we produce 10 different transcripts. Now, how do we compute the uncertainty across those transcripts? First of all, we compute pairwise order rate. So we take each prediction, because here the idea is to look at the prediction that looks more like a target, like a gold transcription. So what we do is we take each prediction, we consider it as our pseudo gold target, and then we compute the word error rate between that target and every other prediction that was obtained. So at the end, we will obtain for each prediction that were obviously taken, considered as a gold target, we will obtain different metrics, because if we do the pairwise word error rate, what's going to happen? We are going to have a list of word error rate, and then we take, for instance, the average. So for the first prediction that is supposedly the target, we will have an average word error rate, and for the second and for the third, and so on until the last one. And for that speech, for a given speech in that setup of AR, what we choose as gold target is the prediction that considered as target gave the the predictions that considered as target gave the less water rate, the lower water rate, the lower average water rate. I don't know if it makes sense. And we then, in the first case where this data is labeled, we add to the initial training data set, we add the corresponding speech and the corresponding gold transcript that we already know. In the context of active learning, what we do is that we obviously take the speech, but then match it with the best predicted output, best predicted transcription. And because we don't want to have some redundancy, obviously, the sample that have been selected, because here, for instance, we use the top K certain samples, the most ones, because we assume that those are the ones that the models struggle more about it. And thinking about the concept of what epistemic uncertainty is, we want to expose the model more to those uncertain samples, and we want the model to be more robust, to be better at capturing them. So those are the ones that we add now to initial training data set, and then we remove it from the augmentation or the pool set, because we don't want redundancy across the different training. So that is overall about that. The active learning part that I described is a little bit new, because is recently I've put that up and came up with that idea. So in the result that I'm going to present, they are not there, but I could also share after some interesting result as well. So what we can see here is that across different domains, I didn't put the average here, but it's on another document. The interesting thing is that across different domains, our approach yield significant improvement. So if you do the average of the baseline and the average of these uncertainty epistemic most, this is where we selected most uncertain samples, and in this case, we've just randomly chosen among the samples in the augmentation or the pool set. So in this case, if you, for instance, do this average and you compare, you will see that these results help actually achieve up to 56% of more improvement of water rate over the different baselines across different domains like the general one and the clinical one, and then also across the both. Both is technically when we combine the general and the clinical domain together as a single data set. Now, to showcase the dataset agnostic nature of our approach, because we didn't want it to be only depending on a single dataset. What we've done was trying three other datasets like Saudi DB, medical speech, common voice, English, accented obviously, so the version is there, and with those different parameters. And what we can see if we do also this average, we can see that the average is also way better. Like if you do the average across these, like 0 0.5, 0 0.3, 0 0.5, and then here you also do these average, you will see that the margin, the ratio of improvement is also up to, I mean, more, I mean, at least 56% of improvement. So we can see that our approach outperforms like all massively pre-trained ASR model, but use way less data, like around 50, 40, 55, 50% less data, and perform well across different domains and like data sets. Another interesting things we've done because of the work, the idea we had was to look at the different accents and how actually the whatever rate, the uncertainty whatever rate was behaving. And remember, I was telling you the definition of the epistemic uncertainty is to have a model that is more certain as it gets fed more data, if I can say so. So ideally, we were looking at the top most uncertain samples accent here in this case. And what we wanted was obviously that as we are moving across the different adaptation round, we want those whatever rate, uncertainty whatever rate to be decreasing. That will be able to show us that our model is getting better actually. And we can notice that trend. For instance, across the general domain, we have exactly what we were expecting. It got a little bit more challenging on the clinical domain because of some other, like the clinical domain is much harder to grasp. The clinical domain is much harder to understand. But after the second round, it was already, if not perfect. And then after when we did like the another adaptation run, it started fluctuating. And this was also reflected in the both, which is like the general and the clinical domain put together. So obviously we did some analysis, and we think that there's a need to have some trade-off across, for instance, how many samples I select across the different um, across the pool or the augmentation set, and how much of like active learning or like adaptation rounds do I perform. But in general, like we can see that our approach is actually allowing to build better and more generalizable ASR in the context of accented African ASR, not only clinical but also general domain, but while actually building and training on very small data set. And it makes it actually very suitable for the African low resource settings, or generally the low resource settings for many other languages. So in conclusion, we've built our multi-runs adaptive learning approach that uses uncertainty sampling to build very data efficient and high performing adapted ASR models that achieve state of the art across um, several models, several domains, several data sets. And obviously also that generalizes well and is like model, domain, and data set agnostics. So as feature was, as I was telling you, we want to explore the different trade-off between adaptation rounds and the number of like the new data points that we need to select at each round. So that's also in the active learning literature is referred to as query size. We will also want to improve the computational complexity and limitation because here what we do is technically as we move from a run to another, we have to restart the training from scratch. And extend these analysis to the phoneme level for better explainability. Since we are talking about speech, then phonemes gives more information about what is happening. So yeah, in general, that is what the work was about. I hope it was insightful, and any all questions are welcome.
Thank you, Bonaventure. I think
You're welcome.
it's a great presentation about the paper. And in the audience, if someone have a question, he or she can drop it on the chat. And Bonaventure will ask to discuss with you. So me, I have a question. I think
Okay.
so. I want to ask: did you try to deploy this model on a real world scenario in some I don't know in some countries in Africa? And did you have some real world solution with this model?
So yes, there's been because we've there's been real world setups where it actually worked, um, maybe even better than what I just presented in the results. For instance, the friends with whom we did this project were um, they evaluated it, for instance, in hospitals in Nigeria, and it was very good. There have been also some works that were like descending from this work. For instance, that was presented at InterSpeech that we call Pretrained ASR model virtual African names. So we use this approach and many others to help pre-train ASR models to better transcribe um, African names. It can be Yoruba names, it can be Wolof names, it can be Igbo names, and so on. So yeah, it's being tested in real life already, and it's been proven to be very efficient. So there was a question in regarding the data set. Yes, the speaker read the same passage. The speaker read the same passages, but then ideally, because they were from different countries, we will have different pronunciations of the same word. So that is where the variability is induced in the data set, and that's probably what makes the task more challenging because you have to learn at the same time to grasp like Igbo accent and at the same time Wolof accent and at the same time Fon accent and at the same time Swahili accent and at the same time Zulu accent and many as well at the same time. But yeah, and there were also various like there were also different domains. Um, you wanted to know if there is an equivalent for the French language of their not that I know of. Not that I know of at the moment. Maybe there is, but I don't know. At least not yet. I think if you guys have questions, you can just unmute your mic and speak. It might
Yes,
be
yes,
better
yes.
than
Also, you
typing.
can yes unmute and speak directly. So I think Amina is asking questions or is on the chat. Um,
Yeah, all of those were English transcripts. Yes, all of those were English transcripts. Yes. So, in the context of healthcare, how crucial is the accuracy and reliability of ASR models when dealing with low risk clinical speech? That is a very good question. I think it is far more crucial because that's a domain where um, these, even the slightest error or mistake can have very high impact and very dramatic consequence. Um, so it's important to have models that are entirely reliable. Accuracy might not be a good metric here because it obviously depends on the task. Sometimes people rely more, for instance, on the recall. Sometimes people rely more on the F1 score. So depending on the task you're working on, you choose the appropriate metric to evaluate the robustness and the feasibility and the performance of your model. But again, it's important to also like perform some, I would say, I'm not an expert of that, some bias and fairness analysis to be able to make sure that the model does not discriminate over certain category of people, whether it's black, whether it's like old people, whether it's people of colors, all those type of things. So there are extra steps that are required to actually make sure on top of the automatic metric that is going to be used to make sure the model is safe and reliable and not biased before being deployed in clinical speech in the healthcare setting. So I think I've already answered that question. No, there isn't. There is no, at the moment, as I know, there is no French language equivalent of the Free Speech 2000 dataset. But that could be something you can work on and provide. That is going to be a good resource for the community. Um, I think a company like, yeah, we work with people from Intron, but the dataset is open. So for instance, you can use it directly from Hugging Face. But yeah, the work has been done with Intron. So the dataset, we worked on it together. I was also on the paper with Intron, and then there have been many other like, let me say, descendant of that paper. So there's been, as I was saying, Afri names, ASR Pretrained model Bircher African names that was presented at EMNO, that was presented at Enter Speech. There have been many others that were accepted at TACO, presented at EMNLP, some that are going to be hopefully presented, including these at EACL or at NACO. So yeah. And so, in your opinion, if we were to make an equivalent for French-speaking African countries, what approach should we use? Collect data, use French data set in the medical field? So this could go many ways. One way way, for instance, will be to, because obviously as I said, the data set is open. So what can be done will be to have French speakers, for instance, French speaker from Benin, French speakers from Senegal, French speakers from Ivory Coast, French speakers from Cameroon, French speakers from Gabon, French speakers from um, Niger, French speakers from um, I don't know, some other French countries, and um, having them read, for instance, those different um, transcripts that you have translated from English to French. That could be a very straightforward. I mean, it's not that straightforward because the amount of effort in that, because you also need to make sure the translation are high quality. The amount of effort is not negligible. So it can be automated because they are good English to French translation systems, but then you also need to perform some human evaluation to make sure everything is in context and not like displaced or like gotten out of context during the process of the translation. And then have that human side which does the recordings for all those transcriptions across all the different speakers and the accent and everything. So that would be a very straightforward approach. But then you can actually also do something completely innovative where you might focus on other domains, but following the same approach, for instance. So in the free speech paper, we described how we actually proceeded. One second, let me copy and paste the. In your free speech paper, we describe how we proceeded, how the data was collected, how the recording was done, and everything. And that might be useful to be applicable to other languages. Can I use the dataset to extract shared features among intra-native speakers? That is, does this dataset contain both native and non-native speakers? Uh, so obviously so here the focus was not really maybe on non-native or native speakers, because we focus on African countries that are English speaking ones. So countries like Nigeria, countries like Ghana, countries like South Africa, and so on. So they are English native speakers, but the way Nigerians speak the English is not the same way um, uh, Ghanaians speak English. It's not the same way South Africans speak English, right? So that's actually what we were mainly focused on, like the different accent, because the way, like if I speak, I'm a French native. I'm from Benin, so the way Benin, as a Benin speaker, the way I would speak French would be very entirely distant from the way someone from, for instance, Cameroon, we speak French, and that determine entirely how you would understand the person, because not only in the way they are speaking, but also it's embeds some, I would say, intrinsic features, like some uh intrinsic I'm lacking the word, some intrinsic um for instance, propositions are a way of like saying things, that are also related maybe to the culture. So there are different aspects of the data set. There are different aspects of this that you could consider, but it was not really between native and non-native. But again, that can be also another way, another like data set, for instance, that could be done. So you could look at, English native speakers, like look at maybe the countries that speak English on the continent, or maybe just use the free speech data set for that side, and try to have the same thing replicated for French native speakers but that speak English. I'm pretty sure there are going to be more of some accent variation inside, and then there you could actually leverage some interesting shared feature among, as you were saying, intra-native speakers. That could be a way of going. But the way currently Afri speech is, we're mainly focused on like the accents among those native English speakers. Okay, so how can we handle ethical consideration and or biases that might arise when training some model on limited clinical data? Because this is a question that often comes up when presenting ASR project on the medical field. So again, I'm not an expert on like bias, fairness, and all those type of things, but from a model perspective, you can always make sure that it's robust. That is one of the thing that our approach is bringing, because we can see that across the clinical domain is doing well, across the general domain is doing well, but then when we combine both is also doing way better. So those are some automatic metrics that tells you, okay, there's some consistency in like everything, and that gives you an idea about how is it performing. But then you might need maybe to perform like more in-depth human evaluations. You might need to work maybe more in-depth closer to some doctors, which actually also we did, because some people in the on the paper, the creation of the data set were actually medical trained medical doctors. And when you test it for instance in real life, it allows you to have some feedbacks. So the model doesn't have to be like deployed directly after the first iteration of the first training. It can be a back and forth, I don't know, 3, 4, 5, or n stages, where you train this and then you go to the practitioners and then you see where the model fails in real life, and then improves it, and then go back and do that repetition over and over and over again until you are sure that it reached a given level of robustness and all like performance. And then here the ethical consideration might also be from different perspective, right? Because it could be, for instance, by making sure that of the type of data you collect and where you collect it from, of the fact that you have to anonymize the data set so that, for instance, patient information are not like released or like extractable. When we talk about bias, the model might be better. For instance, we looked at the top 10 accents. So the model might be doing more mistakes on those accents than the remaining accent. So you might want to understand why, because that means that if someone speaks those accents, you are high likely going to get more errors, more mistakes for us in the medical dictation or the transcription, rather than someone who speak another accent. So you already have in the paper, we already provided those, and then you can base more in-depth analysis on those to actually focus on how and where to improve the model performance, depending on also the target, the audience. So if for instance, you are mostly focused on in Nigeria, so you might want to be making sure that you actually get better at like transcribing or understanding or both English or like samples that are from Nigerian speakers. So yeah, that's what I think. It can come from many angles, as I just described, both from like the sample, the transcript, and the prompt that you collect on the training aspect, and even after. Oh, you're welcome. I hope I was able to at least answer a little bit your question. So, what role does data augmentation play in enhancing the performance of pre-training some model for under resource or domain like clinical speech? Um, so I am pretty sure, as in any domain, data augmentation is helpful, but then not too much data augmentation because it then harm the performance. um so I think it has to depend on like the specific task we are working on, and there should be some trade-off, some amount of data augmentation that is going to be done. So you can have data augmentation from the transcript side, so for instance, we've seen how back translation has been very crucial and has helped like improving and boosting um, machine translation systems performances. So you might have one transcript in, like, let's say English, all those of them are in English, then you might want to translate it back maybe in French and then translate back in English, so you obtain a different transcript that from which you can actually create more audio samples. They are not going to be definitely the same as the initial English sentence. So then you can actually do that, for instance, to get more data and having more context around it. But again, as I say, it really depends on the problem at hand. Uh, but generally, as studies have shown, um, data augmentation should be something that helps the model to perform better. But then there should be some trade-off because too much is going to harm also the model. Yeah, as I said, it won't. In some cases, like you say, sometimes it won't. It actually make the performance either still or worse. So as I said, it really, like, there's no free lunch theorem. Like you're asking what are the most proven effective techniques. There's no free lunch theorem. Generally is supposed to help because it help in fields like machine translations. If you go in other fields, like for instance, self-supervised learning for those type of models that are learning to build um, robust representation from to be able to reconstruct and be able to use solid representation of images, tasks, or like data, for instance, to perform on other downstream tasks. You will see that they are soft augmentations and they are hard augmentations, and depending on the task, some is better. I mean, soft is better, hard is better. Depending on the task, the other ones are actually, I mean, one of those are actually harmful. So I think there's no free lunch theorem. There are many techniques out there to perform some data augmentations, and then depending on the task, you have to try. But then obviously there should also be some intuition why some augmentation would work. For instance, if you are working with like um, I don't know, let's say uh, I don't know, maybe let's say some mammograms, and from a doctor perspective, I'm just taking an example. From a doctor perspective, maybe the image should stay like straight, right, so that you actually look and see the different patterns, the different like things that are in the image that gives you enough information to give you diagnosis. But then if you are performing a data augmentation where you are completely switching it back, and from a doctor perspective, it would not make sense. So that's another type of augmentation you would not do. Even though in sometimes those weird transformation could actually be helpful for the model to distinguish what is good from what is not good. So that's where also I think endowment knowledge is useful to know. Okay, in practice, from a human practitioner side, what makes sense and what does not, and then like see how you can apply that to the task you want to work on or solve.
I think we are running out of time. If there is no more question, we are going to thank Bonaventure for this wonderful presentation, and hopefully we will have it in the next year for
Okay.
another paper. Thank you, Bonaventure.
Thank you so much for having me. Thank you for your questions and thank you for the attention and everything.
Okay, thank you. So thank you everyone, and let's say see you next year.
Yeah. Bye, everyone.
Okay.